In the last video, we discussed how to integrate a vector field along a curve gamma. In this video, we will characterize vector fields whose integral does not really depend on the curve gamma but depends only on the endpoints of the curve. So, for instance, if you have two curves gamma and gamma dash, say the blue curve and the red curve, notice that both the blue curve and the red curve start at P and end at Q. So we are saying that integral of f along gamma should be equal to integral of f along gamma dash. In fact, we would want this property to be satisfied even if gamma and gamma dash were paths and not curves. So we want integral of f along gamma to be equal to integral of f along gamma dash whenever the starting point of gamma is equal to starting point of gamma dash and the ending point of gamma is equal to the ending point of gamma dash. I denote the ending point by t because it's the terminal point. So that's why I am calling it t of gamma and t of gamma dash. So whenever this happens, we want integral of f along gamma to be equal to integral of f along gamma dash. And here gamma and gamma dash are arbitrary paths satisfying this property. We will show in this video that this will happen if and only if f is equal to gradient of phi for some function phi from Rn to R. First, we show that if f is equal to grad phi, then the integral does not depend on the curve you choose, and then we generalize it to paths. More precisely, let f be a vector field, that means it's a function from Rn to Rn, such that f is equal to gradient of phi for some function phi from Rn to R. Then it can be shown that the integral of f along a continuously differentiable curve gamma does not really depend on the curve gamma. It only depends on its endpoints. More precisely, if gamma is a function from the closed interval AB to Rn such that gamma is continuously differentiable, then the integral of f along the curve gamma is equal to phi of gamma of B minus phi of gamma of A. Gamma of B and gamma of A are the endpoints of gamma, and as you can see, the integral depends only on these endpoints. And the proof of this result is quite straightforward. By definition, the integral of f along a curve gamma is equal to integral from A to B f of gamma of t dot gamma dash of t dt. As f is equal to grad phi, f of gamma of t is equal to grad phi at gamma of t. But notice that grad phi at gamma of t dot gamma dash of t is equal to the derivative of the composition of phi and gamma. This is by chain rule. Therefore, we are evaluating integral from A to B, the derivative of phi composed with gamma at t dt. Therefore, by fundamental theorem of calculus, this is equal to phi composed with gamma at B minus phi composed with gamma at A. And thus we have the theorem. By repeatedly applying this theorem n times, we can easily convert this theorem into a similar statement about paths. That is, if f is equal to gradient of phi, then the integral of f along a path does not depend on the path but only depends on its endpoints. Now let us state and prove the converse of the earlier theorem. Let f be a vector field, that means f is a function from Rn to Rn such that the integral of f does not depend on the curve along which you are integrating but only depends on its endpoints. More precisely, integral of f along gamma is equal to integral of f along gamma dash if the starting point of gamma is equal to starting point of gamma dash and the ending point of gamma is equal to ending point of gamma dash. Then there exists some function phi from Rn to R such that f is equal to gradient of phi. Let us now try to see a proof of this fact. As the integral of f is path independent, I can represent integral of f along gamma as integral of f from x to y, where x is the starting point of gamma and y is the ending point of gamma. Then fix an arbitrary point a in Rn and define phi of x to be integral from a to x of f. The claim is that the gradient of phi is equal to f. In other words, the ith partial derivative of phi is equal to the ith component of f. Let us now try to prove this fact. From the definition of partial derivative, the ith partial derivative of phi at the point x is equal to limit h tends to 0, phi of x plus hei minus phi of x whole divided by h. Further notice that phi of x plus hei is equal to integral from a to x plus hei of f, and similarly phi of x is equal to integral from a to x of f. Now, as the integral does not depend on the path, I can choose the path from a to x plus hei as a path that goes via x. In which case, I can split it into two parts, one from a to x and another from x to x plus hei. Therefore, I can write this integral a to x plus hei of f as integral from a to x of f plus integral from x to x plus hei of f. Therefore, this entire expression can be written as limit h tends to 0, 1 by h into integral from x to x plus hei of f. Now I am going to take a specific curve from x to x plus hei, namely gamma from the closed interval 0h to Rn, defined as gamma of t is equal to x plus tei. Notice that gamma dash of t is equal to ei. Therefore, integral from x to x plus h ei of f is equal to integral from 0 to h of f of x plus tei dot ei dt. But notice that f dot ei is equal to fi. Therefore, this integral can be rewritten as limit h tends to 0, 1 by h into integral from 0 to h of fi of x plus tei dt. Therefore, using the second form of the fundamental theorem of calculus, we can show that this is equal to fi of x. That is, the ith partial derivative of phi is equal to the ith component of f. And thus we have proved the theorem we wanted to prove.